Hello, dear students. Hope you are doing well. Today I'm going to start explaining chapter 25, which is the last chapter for this year. It is nuclear chemistry. The objectives that you are going to learn during this session are the following. The first one, explain how an unstable nucleus releases energy. The second one, describe the three main types of nuclear radiation. The third one, describe the type of decay a radioisotope undergoes. The fourth one, solve problems that involve half-life. And the last one, distinguish fission reactions from fusion reactions. Now let's start with the first objective. Explain how an unstable nucleus releases energy. First of all, we want to have a history of a nuclear reaction. In 1896, the French chemist Antoine Henri Becquerel made an accidental discovery. He was studying the ability of uranium salts that had been exposed to sunlight to fog photographic film plates. He discovered that the uranium salts still fog the film in absence of sunlight. So at the end of the time, the Curies were able to show that rays emitted by uranium atoms cause the film to fog. Marie Curie used the term radioactivity. It is the spontaneous emission of rays or particles from certain elements such as uranium. So the rays and particles emitted from a radioactive source are called nuclear radiation. Now, we want to first see the difference between nuclear reactions and chemical reactions. So how do nuclear reactions differ from chemical reactions? So here we have in this figure nuclear reactions that occur in the nucleus of the atom, and here we have a chemical reaction where the reaction takes place around the nucleus in the electronic clouds, where electrons are transferring from one atom to another atom to become more stable. So we have, what do we mean by nuclear reactions? It begins with unstable isotopes. Now let's make a quick revision of what do we mean by isotopes. Isotopes if the element has two or more forms with different numbers of neutrons in their nuclei. They are known as isotopes. Now, what do we mean by radioisotope? A radioisotope is an isotope that gives out radioactivity. So, its nucleus is unstable and it becomes stable by giving off heat and radiation, often in the form of alpha particles or beta particles. So, when we say nuclear reactions, it begins with unstable isotope. So a radioisotope, in this case, we say it becomes more stable. One, changes occur in their nuclei. The changes are always accompanied by the emission of large amount of energy and by the emission of rays of radiation. While chemical reactions, atoms tend to attain a more stable electron configuration by transferring or sharing electrons. The second difference is that nuclear reactions are not affected by changes in temperature, pressure, or the presence of catalyst as chemical reactions. And the third one, nuclear reactions of a given radioisotopes cannot be slowed down or speeded up or stopped. Now, what do we mean by radioactive decay of an atom? The reaction here occurs in the nucleus of the atom, and it will emit energy, it will emit radiation and particles. So let's see what do we mean by radioactivity. Radioactivity describes the tiny subatomic particles and high energy rays that are given out by the nuclei at the center of certain sorts of atoms. So, a radioactive decay is a spontaneous process that does not require an impact of energy. If the product of a nuclear reaction is unstable, it will decay too. So what do we mean by decay? Here, the unstable atom, it will become, in this case, more stable by emitting radiation. So we say decay or change into a different element. So the process here continues until unstable isotopes of one element are changed or transformed into stable isotopes of a different element. These stable isotopes are not radioactive. Now, the second objective is the effect. Three types to describe the three main types of a nuclear radiation and the effect of an electric field on radiation. So we have here the again, let's say that the radioactivity, it describes the tiny subatomic particles that will particles and with high energy rays that are given out by the nuclei at the center of certain sorts of atoms. So we'll start with the alpha radiation. The alpha radiation here, if you examine well the table, on the right side we have the composition of the alpha radiation. It looks like the helium nucleus. Its symbol is like this alpha, and it is He. The nucleus of it is the same as this particle has the same nucleus as helium, He24, so its charge is 2 plus and its mass in A and nu is 4. The common source of alpha particle is the radium of mass 226, and the penetrating power is very low. It is 0.05 millimeter in the body tissue. Example of the alpha radiation, we have here the nuclear reaction. You have the uranium of mass 238. It is unstable in nucleus. It will it undergoes nuclear reaction. It decays. It means it changes into another nucleus, which is here thorium of mass 234, by emitting alpha particles, or alpha emission, which is He24. Now the second radiation, it is called beta radiation. Look again at the table. on the right side, the composition of the beta radiation is exactly like an electron. It is represented as B, beta, and it is symbol is E -10. The charge is 1 minus. The mass is in AMU is 1 over 1837, which is very, very small, and it is approximately 0. The common source is carbon 14, and the penetrating power is moderate, 4 millimeter in the body tissue. Now, in reality, what happens in the nucleus? Here, an electron resulting from the breaking apart of a neutron in an atom is called a beta particle. How the reaction is taking place in the nucleus? In the nucleus, you have a neutron and the protons. The neutron, it will change to proton by emitting a radiation that is the beta particle to the outside of the nucleus, which is the electron E -10. Again, you have in the nucleus, the neutron is the nucleus is unstable nucleus. The neutron here will emit the electron, which is the beta particle, outside the nucleus, and by changing and giving also a proton in the nucleus. So example of the beta radiation, the carbon 614, it will emit the beta radiation, which is the E -10, and this carbon will become another atom which is more stable of a nucleus, which is the nitrogen 714. The third radiation is the gamma radiation. If you look at the table also, you have the composition of the gamma. It is high energy electromagnetic radiation. It resembles the light. Its symbol is gamma. It has no charge. It has no mass. The common source is the cobalt 60. The penetrating power is very high. It penetrates the body easily. So what is a gamma radiation? A high energy photon emitted by a radioisotope is called a gamma ray. They are a form of electromagnetic radiation. Example of the gamma ray, we see here the nuclear reaction. You have the thorium 230, it will give radon of 226, and it will emit the alpha particle with the gamma particle, which is the gamma ray. Now, what is the effect of an electric field on radiation? Let's see it by a photo. Here, a graph. We have the lead block. In the lead block, we have the radioactive substance, which is uranium. The uranium, as we said, emits radiation. We have here electrically charged plates, positive and negative. We observe that rays are passing through the hole here, and we have rays that deviate to the positive plate. So in this case, we say that they are negatively charged. They are the beta rays, and the rays that deviate to the negative plates, they are positively charged. They are the alpha rays, and there are rays that pass through without any deviation, so we call them the gamma rays. We have also here, we explained the penetration of these particles. We said that the alpha particles are the least penetrating and the gamma rays are the most penetrating rays. Let's see here also in the figure, we have the same uranium source, uranium substance that gives radioactive source. We have the three particles that are emitted from the uranium atom. So we see here that the alpha will be stopped by the paper, where the two other rays, the beta and the gamma, pass through the paper, but the beta rays, they stopped by the wood, and the gamma ray, it continues their penetration, where it will stop at by the lead or concrete here. So the penetration of the gamma rays is is the most penetrating one, while the alpha particles are the least penetrating particle. Now, how do we balance nuclear equations? We have to keep in our minds that in a balanced nuclear equation, the sum of the mass numbers and the sum of the atomic numbers for the nuclei of the reactants and the products must be equal. So, we have here the mass numbers. We have on the reactant side, you have the atom which is CF. It has a mass of 251. It should be on the product side, the total mass 251. So we add the mass of the atom, which is Cm, which is more stable than the Cf, by emitting the alpha particle. So we add the 247, the mass of the Cm, plus 4, which is the mass of the alpha particle. We get also 251. So here we say it is the mass conservation. Now, while the atomic numbers also should be the same, we say here atomic conservation. So we have the chart, or we say here the atomic number of the CF is 98. On the product side, we have 96 of the Cm plus 2 of the alpha particles. They are 96 plus 2, we get also 98. So we have here the mass numbers, the sum of the mass numbers and the sum of the atomic numbers for the nuclei of the reactants and the products must be equal. So keep this in your mind. Now, the third objective, which is what determines the type of decay a radioisotope undergoes. Let's make a quick revision. What do we mean by a radioisotope? A radioisotope is an isotope that gives out radioactivity. Okay, and in this case the nucleus is unstable and it becomes stable by giving off heat and radiation. Now, how do we know that this atom is stable and the other atom is not stable? So we have to take the ratio here, the ratio of a neutron to proton. In a radioisotope, it determines the type of decay that occurs. And we said, what do we mean by decay? Decay, it means we have a change in the nucleus, a change in the nucleus of the atom, and it gives another element, or it gives another nucleus or another atom. Okay, so let's see here the nuclear transformations. we have a graph here that explains the stability of a nucleus that depends on the ratio of neutrons to protons. The stable nucleus, it has the ratio of a neutron to proton is 1 or approximately equal to 1. So we have to divide the elements into two categories: elements of low atomic number below 20. This ratio is about 1, or we say here, as you see in the graph, 1 or 1.2 or 1.3. Here we have a band of stability. The nucleus is stable. Now, above atomic number 20, the stable nuclei have more neutrons than protons. So in this case, it will not be, it can give, or it can undergoes, we say here, a nuclear reaction, or it will become unstable. Now, what do we mean by half-life? This is the fourth objective. A half-life is the time required for 1/2 of a nuclei in a radioisotope sample to decay to products. So we have here the half-life of a radioactive element is the time taken for half of it to decay or change into a different element. It decays because it is unstable and particles from the nucleus at the center of each atom escape. Some materials have half-lives of a fraction of a second. Other materials have half-lives lasting millions of years, so their effect will be felt for a long time. Now, how to solve the half-life? We have here the period, which is represented by capital T, is the total half-lives. We have the n, small n, which is the total number of half-lives. So the period, which is the total half-lives, equal to half-life, which is represented by T half, times n. And we have here the formula. The mass remained of the atom, of a radioactive atom, is equal to the mass initial over 2 to power n. Or we can say the A, which is the mass remained, equal to AI, which is the mass initial, times half to the power n. Let's take an example to understand it more. Carbon-14 emits beta radiation and decays with a half-life of 5,730 years. Assume you start with a mass of 2.00 times 10 to power minus 12 gram of carbon-14. The question here, how long is 3 half-lives? The T, capital T, which is the period, equal T half times n. So we substitute here the given. We have the half-life is 5,730 times the 3 half-lives. It is equal to 17,190 years. Now the second question, how many grams of the isotope remain at the end of the 3 half-lives? We apply the formula here, which is the mass remained equal mass initial times half to the power n. The n here is 3, and we get 2.5 times 10 to power minus 13 gram. Now let's explain now the last objective, which is a nuclear fission. The nuclear fission here is when the nuclei of certain isotopes are bombarded with the neutrons. The nuclei split into smaller fragments. This process is called fission. The nuclear fission diagram, we have here the uranium, which is unstable in nucleus, has unstable nucleus, is bombarded with a neutron here, neutron 01. It will give uranium of mass 236, and this uranium is going to split into two nuclei. We have the Kr and the Ba plus 3 neutrons plus a great amount of energy. Now, what do you mean by nuclear fusion? In nuclear fusion here occurs when nuclei combine to produce a nucleus of a greater mass. In solar fusion, hydrogen nuclei, protons fuse to make a helium nuclei. So you have the hydrogen, which is 1, 2, it is the deuterium, plus the tritium, which is 1, 3, it will give the helium 2, 4 plus a neutron plus great amount of energy. Here, fusion reactions in which small nuclei combine release much more energy than fission reactions in which large nuclei split apart and form smaller nuclei. So here we have the deuterium, which is the H12, combined with tritium, which is the H13. They combine together to give helium of 2, 4 plus a great amount of energy plus neutron. Now, how can we make comparison between fission and diffusion? In fission, we have one nucleus split into two nuclei with a great amount of energy, while fusion, two nuclei combine together to form one nucleus. Now, the hydrogen bomb here is the most powerful kind of a nuclear weapon. It works by releasing a large amount of nuclear energy. So, the first nuclear weapons were made in the United States in 1945. They used the energy released when the nucleus of a heavy atom, such as uranium, splits in two. This is called the nuclear fission. It releases particles called the neutrons, which strike other heavy nuclei and make them split in their turn. This process is called a chain reaction. It was this type of a nuclear weapon, sometimes called an atom bomb, which was dropped on the Japanese cities of Hiroshima and Nagasaki in 1945. And in the Second World War, atom bombs have a power equivalent to many thousands of tons of ordinary explosive. So a hydrogen bomb uses both fusion and fission. When the nuclei of as we said, when a nuclei of the deuterium and tritium fuse to form the helium nucleus in nuclear fusion, and highly energetic neutron is released, if the neutron subsequently strikes the much larger nucleus of a uranium atom, it splits the atom into two smaller nuclei, which is the atomic fission releasing energy. So I hope that you are enjoyed in this session. Thank you for listening.